You are watching the Tim Kreitz Adventures channel. Welcome.
Okay, thank you all once again for inviting me to give one of the monthly club presentations. I think everybody here knows me, but I'm Tim Kreitz, W5GFO, and tonight's program is electron tubes, how they work. I've been very happy to see more and more of you become interested in older tube-driven radios and also some of the more modern tube-driven RF amplifiers. The idea for this presentation started for me with the discovery of the Namkin radio hoard a few years ago after he passed away. He had thousands upon thousands of tubes in his collection, and in the process of going through all of those items, I heard several people who were helping in those efforts make comments along the lines of, I don't understand what these things are for. Why did he have so many of these? What are they for? What do they do? That was my first inkling that a presentation like this might be in order. Also, in the past several years, I've had questions like, hey Tim, I'm interested in buying this old radio or this old RF tube amp, but I really don't understand how tubes work or how to tune a tube circuit. Can you give me some pointers, etc.? So this presentation is designed to facilitate a little bit of that. We don't have all the time in the world to do this, but we're going to try to briefly touch on the history of the vacuum tube, the basic theory and application, and we'll talk about some of the different types of electron tubes and what they're used for. Before we get underway here, I want to give credit where credit is due. The majority of the material for this presentation was taken from 4 sources. The main one is the 1952 Army Technical Manual entitled Basic Theory and Application of Electron Tubes. If anyone is interested in obtaining a copy of this manual after the presentation, let me know and I'll be glad to put it on the reflector. It does an excellent job of explaining the subject matter without, becoming too heavily mathematical or technical in its language. It's perfect for the beginner, which makes sense because that's who it was intended for to begin with. I also used reference material from the military training films Electron Theory and the Diode Tube, and what was the other one? Electron Tubes, the Triode. Lastly, and most importantly, I borrowed heavily from an excellent online lecture in tube theory that was given by a man who went by the name of Tom Tech Test. Unfortunately, that's all I know about him. His true identity has been very difficult to successfully research, but he is believed to have been an elder PhD in electronics, and many now think that in the years since he originally posted the material, he may have passed away. But it's still all online if you'd like to check it out, and I would be glad to provide that material as well. Okay, here we go. The first experiments that created the electron tube were actually experiments attempting to prevent the filaments of light bulbs from burning out. These tests were initially performed at Edison labs, where they heated the filament of a light bulb after having evacuated the air from inside it. And they then installed a plate in there with the filament. They then applied voltages to the plate, which had a galvanometer connected to it. What they were trying to determine was whether or not by putting a plate in there, they could absorb the electrons gathering around the filament as it heated. The thing was, they didn't really know at the time that they were electrons. We didn't know what electrons were then. They thought they were dealing with some sort of impurities that were being boiled off and caused, the filament to fail. At any rate, via this process, they discovered that there was a small amount of current flowing across that galvanometer. What actually was happening there, electron flow, was later discovered, as we understand it today, by a guy named J.J. Thomson. Electrons were being thermionically emitted by the filament, sometimes called the cathode, and they were being carried over to the plate. This happens with many things in nature when they're heated. Even a campfire will do this to a certain extent. But the process of gathering and moving those electrons from filament to plate was greatly increased inside the vacuum because there were fewer particles to interfere with the process. So One of the next things some brilliant person did was to insert a higher positive voltage onto that plate, and it was discovered that a positive voltage, which was positive relative to the cathode, dramatically increased the current. This first type of electron vacuum tube was called a diode, which means two electrodes. We'll revisit the diode in just a few minutes. Sometime later, a man named Lee DeForest came along, and he was interested in figuring out a way to manipulate the flow of electrons between the cathode and the anode without changing the voltage on the plate. He discovered that if you put a wire coated in special material between the cathode and the plate, then applied a negative or positive bias to that wire, the flow of the negatively charged electrons could be further controlled. And in this process, the tube could be used as an amplifier. This wire was named the control grid, and the resulting tube design was named the triode, meaning, of course, 3 electrodes. Incidentally, and perhaps I should have asked this earlier, but everyone here understands that electrons are negatively charged and opposite polarities attract, right? Okay, good. The caption from the technical manual is right here. By inserting an electrode in the form of a few turns of fine wire between the filament and the plate, the tube was made into an amplifier. The third electrode was called the control grid. It provided the desired amplification by virtue of the fact that a relatively large plate current and voltage, and those changes could be controlled by small variations of control grid voltage without the expenditure of appreciable power in the control circuit. It was much more efficient. Okay, with these two designs in mind, let's talk briefly about the construction and arrangement of most tubes. Here we have a diode tube on the left. This is a directly heated filament in this particular diode. In other words, the filament is the cathode. That's not always the case. If you look at the triode on the right, you can see that in an indirectly heated tube, the filament is placed close to or inside of the cathode material, which is sometimes shaped, as a hollow tube or a C shape. And the cathode becomes heated by the filament indirectly through convection. Indirectly heated tubes are generally less efficient than directly heated tubes, but they work well and they tend to be quite robust, among some other advantages. Also, note that the control grid of the indirectly heated triode on the right has an elliptical helical design. Grids are shaped and spaced differently depending on their desired performance. They are sometimes ovular, they can be circular, there's ladder type, and also spoke type. So we have the filament, the cathode, and these glass stems to hold things like the filament supports. Here's the plate, here's the grid. These pins connect the tube to the rest of the circuit through the tube socket, and this particular piece is called the getter right here. The getter is a component that is coated in special materials such as boron azite. It gets heated from the outside, usually with an induction heater, and it actually flashes a bit like old-style photographic flash powder. The purpose of causing that reaction inside the sealed tube is to eat up any remaining oxygen that might still be in the tube even after they've evacuated it, and increase the tube's performance and lifespan. The condition of the getter is also a generally reliable way to judge the condition of a used tube at a glance, like if you're at a ham fest or something, to judge whether or not it may have become gassy or leaky. So now that we have a basic understanding of how tubes are constructed and how they manipulate electron flow, let's discuss some of the things they can be used for besides an amplifier. For example, one of the other big uses for vacuum tubes, especially in older receivers and transceivers, is as a rectifier. In its simplest design, a diode tube is used in conjunction with a capacitor to quickly rectify alternating current into direct current. If you'll look at the schematic on the right, you'll see an alternating current source, a diode tube, a capacitor, and a load. When the input is positive on the plate relative to the cathode, electrons flow through the capacitor and through the load to the cathode, and then from the cathode over to the plate, and back to the source. This makes the bottom end of this capacitor negative and the top end positive. When the current reverses so that the plate is negative with respect to the cathode, no current flows. So during that part of the alternating cycle, it's as though this becomes an open circuit. During that time, the charge that has been stored in the capacitor can be fed to the load. The load is fed through the tube for the positive half of the cycle, and it's fed out of the capacitor during the negative half of the cycle, thereby changing alternating current into direct current. If you have two diodes and a center tapped transformer, you can set up this kind of circuit, which is a full wave rectifier. In this design, we're charging this capacitor on both the positive half cycle and on the negative half cycle in the same direction. This is done because it produces a steadier DC current. Okay, let's read this caption and then we'll talk about a few of the problems that were encountered with triodes that led to the development of the next tube type we'll discuss, which is the tetrode. Electron tubes are used extensively as amplifiers. A stronger signal voltage may be obtained from the tube than is fed into it. In effect, the tube is a signal voltage magnifier. A signal equal to 1 volt fed into the input system of the amplifying tube may appear as 20 volts at its output. Different arrangements provide for different amounts of signal amplification. And by the way, we use tubes not only as amplifiers and rectifiers, but as AM detector tubes, voltage regulators, although that's generally a special type of gas tube with what's called a cold cathode. FM discriminator tubes, the list goes on and on. It's obviously beyond the scope of this presentation to explain all of them. Okay, let's get back on track here. Electron tube designs, in a sense, much like antennas, tend to be electronic compromises in some cases. Design-wise, you're often trading certain desirable attributes away in order to get other types of desirable attributes, both of which you can't have at the same time. It's also possible to create other problems in that process. Well, this was the case with triodes in particular. What began to happen with this tube as it was used in amplification applications was that as the tube approached saturation, stray capacitance between the plate and the grid began to occur. This obviously caused a lot of problems, including feedback, oscillation, a little distortion, etc. So in order to arrest the unwanted capacitance between the control grid and the plate, what do you think they did? They added another grid. The result is the tetrode. With an average of about 2 picofarads grid plate capacitance in a triode, this value is reduced to approximately 0.01 picofarads or less in a triode. The screen grid accomplishes this by acting as an electrostatic shield between the control grid and the plate, consequently reducing the grid plate capacitance. So this largely solved the capacitance problem, but as I alluded to earlier, caused another problem in the process. The issue was that with a tetrode, as the plate voltage drops past a certain point, the tube starts to become significantly unstable. You can see it here in this graph. If you'll notice, as the plate voltage starts to drop down below 70-ish volts, the tube basically becomes unusable. It's unstable. This is referred to as tetrode nonlinearity. So as a high gain tube, this design works quite well. But when the plate voltage of a tetrode drops to near screen voltage, tremendous amounts of nonlinearity begin to occur. What's happening here is that secondary emission of electrons are being caused by the plate as it reaches a point where it starts bouncing electrons. It can't absorb back into the screen grid. So the solution to this problem, as you might imagine, was to add yet another grid to the tube and create the pentode tube. Okay, we're kind of going down a rabbit hole at this point. I realize that. But we'll conclude here by briefly talking about the performance characteristics of the pentode, which has a control grid, a screen grid, and now a suppressor grid to suppress the aforementioned secondary emissions. This worked by allowing the suppressor to receive cathode potential to block the electrons bouncing off the plate and preventing them from being received by the screen grid. This allowed the pentode to operate stably when higher input was required, but at a lower overall gain. These are good tubes, and lots of popular tubes are pentodes or beam-forming tetrodes, which are drawn schematically just like a pentode. They're both drawn the same way. Pentodes have excellent amplification factor, but are much more prone to producing distortion, which is the design's primary trade-off. So that has to be taken into consideration, obviously, when designing the circuit. However, look how much more stable the pentode is down at lower plate voltages. All right, just to put the plug in the jug here, here is a longer list of just some of the things a vacuum tube can be used for, accompanied by some schematic diagrams of a variety of different tube architectures. If you're interested in these types of older electronics, there is a ton of information out there for you to dig into and learn. I think we got about long enough, but let me turn my recorder around toward you all, and if there are any questions or discussion, we can do that now.
You know, a lot of those big power amplifiers will have those metal ceramic tubes with the heat sink on there. What's really different about that? I mean, they're still just triode or tetrode tubes?
Right, and those spokes a lot of times are the grids, and they're used in different ways. Everybody has at least one tube in your house right now. If you have a microwave oven, you got a tube in your house. The magnetron inside of a microwave oven is that type of tube, and they're fun to play with. There's a guy on YouTube, a kid on YouTube, who makes laser guns with microwave magnetrons, powerful lasers, and he's a hoot to watch. I can't remember what it's called, but we've all seen it at one time or another. He's gotten in trouble a few times from some of the stuff that he's done making lasers out of those. But yeah, those are tubes just the same. They operate on the same basic principle. Yeah. Anything else? All right, that'll do it. Thanks, everybody.
Thank you, Jim.
Thank you.